All right, so in this module, we are going to talk about defect reactions. And so this is looking at those combinations or groupings of defects that will achieve charge neutrality, such as the Schottky defect or a Frankel defect. And we write them in the form of reactions so that we can treat them like chemical reactions and look at mass action and so forth. So that's what we're going to do in this lecture. And we're going to compare it back to chemical reactions, right? So for chemical reactions, we know that we must preserve mass balance, right? That's the first thing we look at when we do chemical reaction. All right. Also, if you're familiar with electrochemistry, these reactions, we must preserve mass, but also charge, right? And we are talking about charged species. You can see in the Kroger-Vink modules that those were charged species. So this is going to be another important concept that we have to look at. And so with defect reactions, we have to consider one more thing. So the first one we have to consider, which we've already talked about, is mass balance, right? So mass cannot be created or destroyed. All right, 2. This is the one we talked about up here for electrochemical reactions. We must preserve charge. So this is electroneutrality. Or charge balance. And so charge cannot be created or destroyed. All right, and the last one, this is the one that doesn't come up in those other two, and this is known as the preservation of regular site ratio. And so let me write that out for you. All right, so this is the new one. So this is tied to our systems, our defect systems, because we are talking about crystal structures and we're talking about crystal lattice sites, interstitials, and vacancies, and all of those different things, right? So what this means is that we must preserve the ratio between the number of regular cation and anion sites and be equal to the ratio of the parent lattice. So we specifically say regular, and so in this case, we're not referring to interstitials. So interstitials are not regular sites. All right, so this is obviously can still be a little bit confusing, so I think it's best just to look at an example. So let's look at an example of this regular site ratio. All right, so let's look at an MO oxide, so just a generic system. So if we add a cation site to the crystal, right? So if we add one more M to this, what this ratio, site ratio, implies is that we would also have to add an anion site. So we can't just add a cation, right? So it's okay to add cation sites, but if we do that, we also have to add an anion site to maintain the site ratio, right? Because we can't have more M sites than O sites and vice versa. So the same thing as if we had something like an M2O, so if we had 2 times metal, we would also have to maintain that specific ratio in any addition or subtraction of sites. So we can kind of formalize this with a generic MX, so MAXB compound. We can formalize that our site ratio would be A times the number of X sites in X site, the number of X atoms in X sites, plus the number of vacancies on the X site, is equal to B times the number of metal sites on the number of metal atoms on metal sites plus vacancy on metal sites. And then the ratio part is that A over B would be equal to MM plus VM over XX plus VX. So this is the ratio that we're talking about. So A over B for these coefficients, and then on the top here we have the number of metal sites plus the number of vacancies, and then X sites plus any vacancies. So that's the ratio of regular sites that we're talking about. So a site is either a vacancy or an atom, and so that's why we have the combination of the two. So it's important to note here that we're not implying that the number of atoms must be maintained, but the number of sites, because we do have to account for vacancies, right? So the number of atoms or ions doesn't have to be maintained, but the number of sites does. All right, so now we're going to kind of look at more specific examples in the next module, specifically stoichiometric defects.